Hello, I am Professor Congleton. This is Econ 421. This is a pre-recorded lecture on an introduction to abstract functional forms, or the calculus of abstract functions. In order to deal with more abstract functions than we've dealt with so far, which have all been members of particularly well-defined and tractable functional families, we need three more ideas from mathematics. Okay, the first is called the sufficiency theorem. The sufficiency theorem says that if you're trying to maximize a function, and you know that the function is strictly concave, and you know that the feasible set is a convex set. A convex set being a set that if you connect any 2 points within the set with a straight line, that all the points on that chord will lie inside the set. So if you have a concave function or strictly concave function in a convex feasible set, then when you go through a Lagrangian optimization or something of that sort, or do a substitution method optimization, the results of the first order condition are sufficient to characterize the optimum of the function you're interested in. And that means that we don't need to be able to figure out specific values for the first order conditions. It's enough to kind of characterize them rather than actually be able to kind of write down specific numbers or even specific equations that represent what's going on. The second theorem that we will make a lot of use of, in fact, more direct use of than the sufficiency theorem, which we use more or less routinely and take for granted in the background, is the implicit function theorem. Well, the implicit function theorem says that if you have a function that has the value 0, no matter what its for, okay, and an example of that would be a first order condition. Okay, first order condition is satisfied when the first derivative is equal to 0. Okay, so first order conditions are often used in this way. Well, it turns out that if you have this function that's equal to 0, that you can always solve for any element of the function, a, b, c, d, or e, any of the variables in that function, as a function for all the other variables. So that means, for example, in the first order condition, if you want to solve for, say, the quantity of x1 demanded, you can break x1 out of that function and write it as a function of all the other parameters of the choice setting. It's very handy. Okay. And because of the sufficiency theorem, we know that what we've done with the first order condition will be sufficient to characterize the optimum. Okay. If you want to be able to do comparative statics after we've done that, then we need to be able to take derivatives of these functions. But these functions are really pretty abstract. Well, it turns out that you can use a rule, a differentiation rule called the implicit function differentiation rule. And as long as this function here is differentiable and has non-zero derivatives, then it's possible to write down the derivatives of, say, suppose I've taken this function and broken a out and solved for a as a function of all the other variables like I did up here. Then if I want to find dA, dB, for example, then what I can do is take the derivative of this function with respect to b and divide it by the negative of dh, this function, with respect to a. And it turns out that that will be the derivative of this function with respect to b. Okay, there are a couple ways to prove that. I think for this mini lecture I won't bother to go through the proof. The proof is in the lecture notes under chapter 11. And you can see how that proof goes through. It's really quite straightforward once you realize this is what's going on. In general, without doing the math, which is not that long actually, if we take the total derivative of this function, it will be, dA, dH, dA times dA, dH, dB times dB, and so forth through. And you add all those up, and that will have to add up to 0. right? And it turns out that if you only want to allow a couple of these variables to change, which is normally what you do when you take a partial derivative, then all the other terms have to be zero. They're not changing. Those changes don't matter. And you can just focus in on those two, and when you solve the algebra for this, you wind up with this expression for what the partial derivative of A with respect to B looks like. And that's quite handy because, again, if this function we're using for this purpose is a first order condition, and we found out the demand curve or demand function for some particular good in that function, well, then it's possible to find out whether the demand curve slopes downward, whether it has a positive income effect, and whether it changes systematically as the prices of substitutes change, and so forth. All those are possible because of this implicit function differentiation rule. And it's these sorts of functions that I've used in most of the theoretical work that I've done in my career, which I probably have 50 or 60 papers that have equations of this form kicking around in one way or another. So what we're going to do today is go through one example, and part of the the purpose of the example is to show you how to deal with the notation of these abstract derivatives that we're going to be working with. So I think I'll start off with that, and then we'll go through the example. Okay, so first some notation. Suppose that u equals some function of two goods, x1 and x2. Right, so that's a way of writing, for example, a Cobb-Douglas utility function, any of those functions that are members of our exponential multiplicative family that we've been using throughout the semester. But also includes lots of other types of functions. Okay, well, if this is a good, then we want to say that du dx1 is greater than 0. Right, so goods have positive marginal utility. And sometimes I write this, and you'll see this in the notes, as ux1. I use a subscript to indicate that this function is this is a derivative of this function. Okay, and there's some other notation that you see occasionally used, but as a rule of thumb, you see either this notation or this notation, both in my notes and in most published work. You occasionally do see some other versions, but these are the most common. So if x1 is a good, then we know that the effect of that good on utility levels should increase as you consume more of it. Okay, and so normally we're going to assume that all these things are goods, although that's not absolutely always the case. Okay, for bads, the reverse holds, right? So we get the u dx3 is less than 0. All right, so notice that we're doing a lot of things abstractly here. We don't know what the function is. You can't write it down in a concrete functional form. We're kind of used to dealing with the quantities of goods in this abstract form. We've used Q and other things like that throughout the semester. We've used X to indicate those quantities. In mathematics, you pick the letters out that you want to for your functions, although there are kind of conventions. Right? So virtually everybody writes a utility function as U. And the quantities of goods, sometimes those are Q's, sometimes those are X's. That's pretty conventional. I know in class I've sometimes used A, B, and C with capitals as when I'm doing Cobb-Douglas or multiplicative functional forms. And in many cases I will name the variables and use letters that remind me of what the name is. So if this X2 is government services, I'll put G there for government services so I can remember what that good is. And so you can, as the reader or student, can also remember. But if I'm just trying to be general, I'll just leave it as X1 or X2. Now, how do you write the second derivative? The second derivative is written as u x1 x1 equals du squared dx1 squared. And that will be less than 0 if x1 exhibits diminishing marginal returns, or utility, I guess, in this case. Right, so again, this is just notation. These are conventions. And it turns out that when we are messing around with derivative of abstract functions, we'll be wanting to use a lot of this notation. Okay. As a rule of thumb, we want to assume that the utility functions are strictly concave, and that will be true if their second derivatives are less than 0. Okay, that's one of the assumptions you need. And it would be true for both this double derivative of x1 and also for the double derivative with respect to x2. Another type of relationship another type of relationship we're interested in when we're dealing with abstract functions is something called cross partials. All right, suppose I have this margin utility curve for x1. And I know that x1's margin utility depends in part on the level of x2 that I have. And that's true for all those exponential functions we've messed around with. There's always been an x2 in that characterization of margin utility of x1 or x and vice versa. Well, if I want to know how this variable affects this margin utility, then I want to look at something called the cross partial. I want to take a look. I want to take this derivative here and take the derivative of it with respect to the other variable I'm interested in here, x2. So if I want to write that in notation terms, I write that u x1 x2, and that's equal to du squared dx1 dx2. Now it turns out that for most purposes it's really convenient to assume that those cross partials are 0 or greater than 0. It turns out that if you have negative second derivatives and positive cross partials, then the function will always be strictly concave. If some of these are negative, some of these cross partials are negative, then the function may or may not be concave. It just depends on how large those effects are compared to the effects of the second derivatives of the variables in the function. Okay, so notice that there's a lot of notation here, right? This is just ways of thinking about things. These are not specific values, right? We don't know what this number is, okay? But it turns out that what we normally do when we work with an abstract function is we give it some shape. If you remember in the second lecture in the course, I talked a bit about shapes of functions. And so that's where we first introduced the idea of strict concavity. And the shapes of functions that are continuous and differentiable can be well characterized with these derivatives. And so as a rule, economists care mostly about the first derivatives, and then the next most important are the second derivatives, including this one here, and the cross partials, which is another type of second derivative. So as a rule of thumb, it's rare to see an economist worry about more than 2 derivatives in a function. In some of the literature on risk, you'll see occasionally people talking about third derivatives and even fourth derivatives, but generally speaking, we don't worry about those, and we certainly won't worry about them in this class, okay? Because mostly we're interested in modeling rational decisions, and we want to be able to use the sufficiency theorem to simplify our lives, so we want to be dealing with strictly concave functions for the most part. For strictly concave functions, typically the first derivatives are positive, second derivative is negative, cross partials are usually positive or zero. Now, if the cross partials are zero, then the function is said to be separable. Okay, so a function that is separable looks kind of like this. Right. So, for example, if I wrote down a utility function that was h of x1 plus g of x2, those two little functions would characterize how one variable affects overall utility. And because these are kind of additive rather than multiplicative, there's no interaction between those two functions. And so those cross partials will be zero. And you'll see those functions are often used in economic model building because they make the math a lot easier. Not because the authors necessarily believe the world is separable like that, but because for the purposes of the paper, they don't believe, and sometimes they're wrong, of course, that these interdependencies are all that important to understand the basic phenomena, basic relationship that they're interested in highlighting with their model. Okay, so once we know all this, we're actually in a position to start thinking about specific types of derivatives. Right? So for example, if I had a derivative and I had a function in here instead of x1, suppose this x1 was a function of some other thing like z. Okay, well then in order to calculate du dx1, I would need to take account of both the importance of x1 to utility and the importance of z to x1. And so that sort of function, and we just let's make this one, let's make it g of x2. Right, so I may still be interested in this partial derivative to u dx. That's supposed to be a u. But it may be that x is not the direct thing argument in the utility function, and instead it's g, but g itself is a function of x. Okay, and so I can still find out what du dx2 looks like. Okay, but I have to first find the partial derivative with respect to this argument, which I've called g, and then I want to find the change in that argument, g, that's associated with x2. And so that's why we do something that's essentially just an implementation of the composite function rule. And we'll do a lot of that stuff, and it makes some of these derivatives get really messy. On the other hand, a lot of times the results are really sharp and fast, and you can dig them out with this type of technique much faster than you can with Lagrange, and use general functions to do so. So what I'm going to do next is to go through a little bit of the theory of demand, very similar to what I did in the last lecture, but I'm going to do it with abstract functional forms, namely this one. And we're going to use the substitution method for the first time in quite a long time to start the problem up. We've used the substitution method many times in the middle of our algebraic derivations, but this will be the first time that I can remember since the first couple of lectures that we've used it other than perhaps in the duopoly examples, where we substituted for price into the profit equation for the duopolists. Okay, so let's let u be u of x1 comma x2, and w equals p1 x1 plus p2 x2. Note that this expression can be used to characterize x2. So it implies that x2 is w minus p1 x1 over p2. Right? So I'm just solving this equation for x2. And then I can substitute for x2, right, in that slot there in the utility function, and I get u equals u of x1 comma w minus p1 x1 over p2, which includes the constraint. All right, so I don't need to do Lagrange because I now have a function that automatically takes account of the constraint. And notice that this function has only one control variable in it. Right? And you notice that during the semester we've been talking about control variables quite a bit. When you deal with abstract functions, it's important to remember which variables are control variables and which are kind of exogenous to the person making the decision, which are parameters of its choice problem that it has no control over. In this case, the choice variable is x1, and the variables that he doesn't have control over are w and p2 and p1. So I can maximize utility using the same type of notation that we had before, but now I'm going to be working with an abstract functional form instead of a concrete functional form. So we want to take the derivative of utility with respect to x1. And the way you do that for this kind of abstract function is like this. You do du dx1, right? That's the derivative of utility with respect to this variable, plus the derivative of this utility function with respect to x2. But now since we're doing x1, you can see x1 is over here causing x2 to have particular values. So we're going to be having du dx2, like we did in the previous illustration, times the derivative of what's inside. Well, the function inside is concrete in this case, rather than abstract, like it was when I put up that composite function rule a second ago with g of x2. If I take the derivative of this guy with respect to x1, it's going to be minus p1 over p2. And we're going to set that equal to 0. And that will be our first order condition. Now the implicit function theorem implies that there exists a function, you can name it whatever you want to, that where you isolate any one of the variables in this guy, and you have to remember that there are some variables that aren't actually completely evident, and we'll talk about that in a second, but it's going to be w, p1, p2, And the reason W shows up in this list but isn't obvious here is that this function, U prime, is some kind of function of the same arguments as the original function, which was x1, and that substitution p1 minus, w minus p1 x1 over p2. Right, so each one of these partial derivatives are functions, and when you're dealing with the abstract forms, the functions have the same arguments as the original objective function. Right, they have x1 and this w minus p1 x1 over p2 as arguments. Or you can think of it as x1 and x2, where x2 is being characterized now as a function of x1. Right, so if you look at this guy, here's an x1. Okay, that's a control variable. Parameters are w, p1, p2. And those are what show up over here in the implicit function rule. And this is the demand function for good 1. Now notice that to derive the demand function in this way is 2 lines. Maybe 3 lines, depending on if you count figuring out what to substitute into the utility function to describe the path of good 2, of x2. But basically, you do that, you take the derivative, set it equal to 0, and then apply the implicit function theorem, and you've got a nice, neat characterization of the demand curve. Of course, you don't know too much about what that demand curve looks like now at this point. But that can be figured out. Okay. Remember, this is a function that's equal to 0. So suppose we call that h. Well, the x1, the p1 is going to be dh dp1 over dh dx minus dh dx. Right, that's the implicit function differentiation rule. Now, you can use the implicit function differentiation rule on lots of functions. You can use them on concrete functions as well as abstract functions. Occasionally, when you get a first order condition, there's no really clean solution that will get you to a demand function like this. So you can just, because you've got a function, even though it's in concrete form, that's equal to 0, you could still use this theorem to characterize the function in a general way. And you can still use these derivative rules to take derivatives of this monster that you haven't been able to solve for x1. Okay, it will still work. All right, so these are tools that you can use on a variety of functions, not just the very abstract ones that I'm illustrating for you right now. And occasionally, if you have that filed away in the back of your mind, when you're trying to model something like in your term papers, you may find one of these tools to be useful. Okay, even though you aren't trying to do something as abstract as what I'm going through now and will be going through for the rest of the semester. Okay, so how do you do these guys? Okay, well, it's tricky. Okay, so I guess this is x1. So if we focus, as it turns out, this derivative, the h dx1, is really the second derivative of our original function, right? And the second derivative of our original function is going to have a negative value if we've got a strictly concave function. And if I've assumed enough stuff to make that so, then I won't have to worry about the denominator very often if all I want to do is to figure out whether the demand curve sloped downward or not. If I want to know how fast, then I need to figure out both parts of this fraction. Okay, but generally speaking, if the function is strictly concave, then dh dx1 is going to be negative. No matter how messy it looks, it will be negative. And usually you can actually determine that with the math. And then minus times a negative is going to be a positive. So whatever the sign of the numerator is winds up being the sign of the partial derivative you're interested in. Here, what the slope of the demand curve looks like. Okay, so I'm going to go through the numerator now. And in class, when I get back from Japan, I'll go through another example and show you what the denominator looks like. In the web notes for this lecture, chapter 11, you'll see this worked out in long form, although I only go through step by step to get the numerator, because once you see how to do it, you should be able to work through the denominator as well. It takes a while to do these things, especially the first time you try, because it's so abstract. And there's so much notation involved. And the trick is not to get lost. And remember that some of this is just notation, but then once you've got all the notation down correctly, you can go back to your original assumptions about derivatives of the utility function, shape of the budget constraint, and stuff like that. And you can figure out what the signs of each term winds up being. And then when you evaluate the whole string of terms, you often, although not always, can determine what the sign is, even though you don't know very much about the functions themselves. So let's try to get the HDP1 and see what that looks like. Okay, so notice I left this line here on the whiteboard because I need it. Okay, I can't keep all this stuff in my head. Remember that this has two arguments in it. The first one is x1, and the second one is x2. And the only place where p1 shows up is in the second argument. So the only place I have to worry about when I take this derivative of this term with respect to p is that second argument. So how do I write that derivative? That derivative is du dx1 dx2 times the derivative of the inside. Right, so the derivative of this term with respect to p looks like this. But we also know what this thing looks like, right? This function x2 is w minus p1 x1 over p2. So when we take the derivative of this guy with respect to p1, we get a specific functional form. We get minus x1 over p2. Right, so I can, once you have that in your head, I can just get rid of that term and write in what it is algebraically or according to calculus, minus x1 over p2. Right, and that's the first term. Okay, the second term has p1s in the product as a product with the other derivative. So we're going to have to use the product rule on this. And so that means we're going to get at least two terms when we take a derivative of this term with respect to p1. The other place we're going to find p1 is in the second location of this function, right? Again, each of these partial derivatives is itself a function and has the same arguments as the original function, the original objective function, the parent function, if you want. And so how do I write the second derivative of the second one? I'm going to be doing a kind of similar thing. I'm going to have du dx2 dx2, which is x2 squared, right? So we can just write that as like that. All right, that's the derivative of that term. And then remember the other thing is going to be dx2 dx1, or dp, pardon me, dp1, because that's where the price is. And then there'll be this other term using the multiplication rule, minus p2 over, or pardon me, minus p1 over p2. Well, that is going to be the same as this one, right? Because we did the same thing over here. So again, remembering what that functional form looks like, x2 equals w minus p1 x1 over p2. So when we take the derivative of that with respect to P1, we get minus x1 over P2 again. Right, same as we got over here. Now we're doing the product rule, so this is the derivative of the first term times the second term, and then we're going to have to do the derivative of the second term times the first term. So we're going to another term plus du dx2, that's the first term, times the product of the second term minus 1 over P2. Okay. So that's the HDP1. Now I said we could probably sign that if we make the assumption that the cross partial, which is what this is positive, then we're okay here. Then we have a negative sign here. So the first term is negative. We have a second derivative here that's usually negative. That's a negative. And that's a negative, right? So this whole term is negative. And this is what? It's positive, and that's negative. So the whole term is negative. So the whole thing is less than 0. So if you trust me on the denominator, that the denominator is going to be negative because we've assumed enough to make everything strictly concave, then we know that that ratio, dh dp over minus dh dx1, that whole thing is going to be less than 0. Right, and that means what? It means that the demand curves with these properties, based on utility functions with particular properties, mainly that they're strictly concave, basically, have downward sloping demand curves. Okay, so in intermediate micro, you learned that you can't always tell that because of income and substitution effects. Where are those things running around in this model? Well, it's not clear. The only place that they seem to be is in these cross partials. So making the assumption that the cross partials are either 0, function separable, or they're positive are sufficient to cause demand curves to slope downward. And that's a good reason to start your models with that assumption if you do them in this abstract form. So I think that's enough for a pre-recorded lecture. I generally like these to be shorter than the in-class lectures. I do cover a little bit less in these than in the in-class lectures, but on the other hand, I'm not hesitating to watch and make sure you're writing your notes down, you're through writing your notes before I move on to the next point. I'm trusting you to hit the pause button or and jot down whatever you want from the screen or from my remarks before activating the lecture up again and proceeding. And so the other thing is, of course, that's not happening is I'm not getting any questions. And so the whole lecture goes faster. So even though I cut the lecture back in time, say by half, I probably am still covering 3/4 as much as I would in class. It's just there are fewer hesitations and unfortunately no questions. And as I said last time, these are imperfect substitutes for what we have in class, but it's a lot better than nothing. And so that's what we're doing to fill in while I'm on my way to Japan or giving lectures over there. Engaging in outreach for the university to some extent. So with that, we'll stop for today, and the next lecture will be a live one in class after Thanksgiving. So have a nice Thanksgiving holiday, assuming you glance at these pre-recorded lectures on Thursday or over the weekend before you go home. And if you are home while looking at this, have fun going back to your friends and family after you take a look at this lecture. So I'll see you on the Tuesday after Thanksgiving. Thanks.